We've got one more big term to define in this section. The point where a graph changes concavity, so this is just saying where it changes from being concave up to concave down or vice versa, is called an inflection point. So if my graph changes from being concave upward to being concave downward, then I have an inflection point at that exact x value. Same thing if I change from being concave downward to being concave upward, we have an inflection point wherever that change occurs. This is similar to local extrema in that we're really paying attention to where does the sign of the second derivative change, but it's a little bit different in that we only have this one single definition of an inflection point, and we're just looking for any change. We're not necessarily looking for is it changing from positive to negative or negative to positive. It's just as long as there's a change, that's an inflection point. So let's look at an example. Let's find the inflection points of f of x equals x cubed minus 9x squared plus 24x minus 10. So I'm going to start the same way that I've started. If I want to determine concavity, I need to find the second derivative. In order to find the second derivative, I need to start with the first derivative. So I'm going to find f prime of x first. F prime of x is x cubed, 3x squared. Let's say 3x squared minus 18x plus 24. So there's my first derivative, but I want concavity, so I really want the second derivative. So f double prime of x is equal to 6x minus 18. And just like we've done in almost every single other example, I'm going to find places where f double prime of x is equal to 0 and places where f double prime of x does not exist. So places where f double prime of x is equal to 0, take my second derivative, 6x minus 18, set it equal to 0, we can solve for x here. So 6x equals 18 gives me x equals 3 as a partition number, so that's good. The other thing I need to check is, hey, where does my second derivative not exist? So where does 6x minus 18 not exist? But f double prime is a polynomial, so it exists everywhere. Means that if I try to find x values where the second derivative does not exist, I'm going to have a really hard time because there are none. So the only partition number that we need to worry about is x equals 3. So okay, we've got our partition number. Let's construct our number line here. I'm going to say here's f double prime of x, and I'm going to place 3 on that number line. So just like we've been doing, take a number on the left-hand side of 3, take a number on the right-hand side of 3, plug those into your second derivative here, and then let's determine the concavity. And then once we have the concavity, we can determine if there is a change in that concavity. That's what we're looking for. So first I need a number on the left-hand side of 3. I'm going to pick 2. F double prime of 2 is equal to 6 times 2 minus 18. This is 12 minus 18, or negative 6. So my second derivative is negative on the left-hand side of 3, which means it's concave downward. And let's erase this just so that we don't get too confused. Now I need a number on the right-hand side of 3. One thing that I'll actually go out of my way to mention here, I can't just assume that it's going to be positive over here. I need to actually show that there is, in fact, a sign change at 3. So I do still have to take a number over here on the right-hand side of 3 and plug that into my second derivative. So I'm going to take 4, f double prime of 4, is equal to 6 times 4 minus 18. This is 24 minus 18. This time I do get back a positive 6. So my second derivative is positive on the right-hand side. If my second derivative is positive, then my function is concave upward. So I'm going to draw a picture of a concave upward function. And at this point, now I should be able to look at my number line and determine, are there any changes in sign? Yeah, absolutely. Look at 3. There's a big change in sign right there. Changes from negative to positive. So again, like we said, we don't care whether we're changing from negative to positive or positive to negative. As long as we identify some sort of sign change, that's going to be the location of an inflection point. One last thing I need to do, I know that at x equals 3 I'm going to have an inflection point, but it's an inflection point, meaning I want the coordinates of the point there, meaning I want the x value and the y value as well. So for my last step, I'm going to take that x equals 3 and plug that into my original function f of x in order to find the y value. So f of 3, this is equal to 3 to the third minus 9 times 3 squared plus 24 times 3 minus 10. So let's see, I've got 27 minus, this will be 9 minus 81 plus 24 times 3, that should be 72 minus 10. So let's see, this will be negative 9, negative 81 plus 72, that'll be a negative 9 minus 10 is negative 19 plus 27, I should have a positive 8. So that means I have an inflection point at 3, 8. Or you can say at f of 3 is equal to 8. Usually for inflection points, I will just give the ordered pair. So I'll just say, hey, I have an inflection point at 3, 8. Let's look at one more example and kind of put all of this together. So here, I want to find the intervals where my graph of f is concave upward, where is it concave downward, where are the inflection points, and here is my function, f of x equals e to the 3x power minus 9 times e to the x power. So, okay, if I want to describe concavity, inflection points, all of this is really referring to the second derivative. So I need to start by finding my first derivative. So first I see derivative of e to the 3x. This is going to be a chain rule here because of this 3x in my power of the exponential. So remember the derivative, if y equals e to the u, then y prime is u prime times e to the u. So the derivative of 3x, that's just 3 times e to the 3x power, minus, here I don't have a chain rule for this 9e to the x because that power is simply just x. That's not going to be a problem for us. So minus 9e to the x. But I wanted the second derivative, so I need to take the derivative again, so f double prime of x. Again, this is going to be a chain rule. So let's see, I'll have 3 times 3, so I should have 9e to the 3x power minus 9e to the x. So all right, here is my second derivative. I would like to find partition numbers for the second derivative. So I'm thinking about where is this second derivative equal to 0? Where is this second derivative undefined? Where does it not exist? Let's take this case first like we normally do. I'm going to take 9e to the 3x minus 9e to the x and set this function equal to 0. And let me just erase this to give myself more room. Here's where factoring is really going to help us out. When I look at this, there's really not a great way to solve this, I think, other than to factor. I am going to factor out 9e to the x from both of those terms. That will leave me with e to the 2x minus 1 is equal to 0. I'm going to now take each factor and set it equal to 0. So 9e to the x is equal to 0, and e to the 2x minus 1 is equal to 0. On the left-hand side, I'll start by dividing by 9, so I end up with e to the x equals 0. Hopefully this looks pretty familiar to the last problem we did in the previous video, because if I try to take the natural log of both sides, natural log of 0 does not exist. It's out of the domain of the natural log function, which means that this equation has no solutions. But that's okay, because I have this other one I can think about. I'm going to add 1, e to the 2x is equal to 1. Here I can take the natural log of both sides, so I'm going to take natural log of e to the 2x and natural log of 1, because 1 is in the domain of natural log. On the left-hand side, I'll have 2x, and on the right-hand side, natural log of 1, that is simply 0. I end up with x equals 0. So all of that was just for this first case, though, for where f double prime of x is equal to 0. I do also want to continue the habit of thinking about where does the second derivative not exist. Is that going to cause problems for us? Are there other partition numbers that we need to think about? But here in this case, I can look at this and say the the domain of 9e to the 3x is negative infinity to positive infinity. It's not going to be a problem. The domain of 9e to the x, then, same thing. The domain of that is negative infinity to positive infinity. Not going to be a problem. So we don't really need to worry about this case here. We don't need to worry about places where f double prime of x does not exist, because it exists everywhere. So I'm going to erase it just to give myself a little bit more room. I have my partition numbers, so why don't we construct our number line for the second derivative? So here's f double prime. The one partition number we came up with was 0. And I'm going to take numbers on either side of 0 and plug those into my second derivative over here. So why don't we start with negative 1. Let's see, this is f double prime of negative 1. This is 9e to the 3 times negative 1 minus 9e to the negative 1. So this is really 9e to the minus 3 power minus 9e to the negative first power. And let's see, this guy should be bigger, so it's going to be concave downward over here. Let me just double check. I do have a graphing calculator in front of me. Minus 9e to the negative first power, negative 2.86 if you really want to get a graphing or get a decimal approximation. You could just look at these two numbers, decide which one is bigger, and then take the sign of the result. Here, negative 9e to the negative first, that's bigger, which is why we ended up with a negative number. But we ended up with a negative. That's what we really care about. I have a negative second derivative on the left-hand side, which means it is concave downward on the left-hand side of 0. And I'm going to do the same thing on the right-hand side now. I'm going to pick, let's say, 1. F double prime of 1, this is 9e to the 3 times 1 power minus 9e to the first power. So this is 9e to the third minus 9e. So actually, we can simplify this fairly easily. This is 9e squared. And I can look at this and say, well, 9 is a positive number. E squared is a positive number. When I take two positive numbers and multiply them together, I'll get another positive. But if you'd like a decimal approximation, you can also get that as well. Here I have 66.50 if you round to 2 decimal places. But in either case, it's positive. So my second derivative is positive on the right-hand side of 0, which means our function, f of x, is concave upward on that region. So, okay, we're just about done. Let's erase this. Actually, here, let's just section off a spot where, oops, oh my goodness. How do I stop this madness? There we go. Okay. Let's section off a little spot right here where we can put our answer. We can now say, okay, this is concave up wherever the second derivative was positive. Well, it's positive on the right-hand side of 0. So on 0 to positive infinity, it is concave upward. On the left-hand side, our second derivative is negative. That means our function is concave downward on that region, on negative infinity to 0. And again, I want to look for, do I have any sign changes? Well, I'm changing from negative to positive. That is absolutely a sign change, which means that at 0, I have an inflection point. So, okay, I have an inflection point at 0. The last thing that we want to do then is find the y value that corresponds to that. So I'm just going to kind of squeeze it in right here. F of 0 is equal to e to the 3 times 0 minus 9e to the 0. I'm just plugging my x value of 0 into my original function to find the y value. So this will be 1 minus 9 times 1, which will give me negative 8. So I have an inflection point at 0, negative 8. So this is everything that the problem has asked me for. I've determined where my function is concave up. I've determined where my function is concave down. One last thing that I'd like to mention here about this example is that when you graph inflection points, they can be quite a bit more subtle than, say, local extrema. Local extrema, I think, are usually easy to pick out. If you showed a picture, with a maximum to somebody who didn't know anything about math, they might be able to look at that and kind of pick out that important point. Inflection points are a little bit more subtle. When you have an inflection point, you may see something like this. Actually, we saw something like this a lot in the last section where he said, hey, this turning point, that seems important. And well, now we can talk about why that is. Look at how this graph opens on the left-hand side over here. It's concave downward on that left-hand side versus on the right-hand side, my graph is concave upward, which means right here at this turning point that we identified earlier, that is actually an inflection point. So we have these instances where we may have, say, a first derivative of 0 because we have a horizontal tangent line right there. It's neither a maximum nor a minimum, but it is an inflection point. So these are going to be a little bit harder to pick out if you're looking at the graphs. Luckily for us, I'm not going to ask you to do that, but we will have to know how to sketch them, and we'll talk about that in more detail in the next video because we're going to focus really closely on putting together all of the tools that we've learned from 4.1 and 4.2 and see if we can't use those to help us sketch the graphs of functions.